Okay, this is going to be a displacement example with 3 different displacements here, and I'm going to use the component method to find the total displacement. Just going to do a little diagram here. I'm going to give each of these displacements their own little color, and that way we can hopefully keep them straight. So 2.1 kilometers north, 30 degrees east. So I go north, and then I go east, and my 30 degrees goes where I start. So when you draw these diagrams, you always go with the first, then the second, and you put your angle where you started your vector. And then the size of the vector is the hypotenuse, so that's 2.1 kilometers. Then the hiker is going to go 1.5 kilometers east. So there's your 1.5 kilometers east. And then west 20 degrees south, so right across everything I've done here, but that's okay. I'm going to change this color. I'd like it to be red. There we go. So west 20 degrees south, so a little bit south. So like that. Right in there, I've left myself enough space, but that's 20 degrees and 1.5 kilometers. So what I'm interested in for my total displacement is from where I started to where I finished. What we can see here, and I've done this intentionally, is we've got a quadrilateral. We don't have a triangle. So we can't use the sine law. We can't use the cosine law directly. Now, if you're really thinking, we could use the sine law to solve for 2 of them and then do the third one, but that's getting into be quite a lot of work. And now I think our component method is going to be a little bit easier. So let's break these vectors up. Let's go with delta d1 first, and then we'll go with delta d2 and then delta d3. So delta d1, that's my green guy here, goes north, then east, with an angle of 30 degrees. And I have 2.1 kilometers of distance. This is my hypotenuse, this is my opposite, and this is my adjacent. So to get my 2 components, I can call this my d1n component, or the north component. I can call this d1 east, obviously the east part of this. Then for d1n, I have my adjacent and my hypotenuse, so I'm going to use the cosine ratio. And if I substitute, cos 30 then is going to be equal to d1n divided by 2.1 kilometers. Multiplying both sides by 2.1. And this is the same step you seem to always be getting to, right? Where you've got your number times the cosine or the sine of the angle. So if you want to skip to that step, that's okay. But because this is the first example, I'm going to obviously take the time to do it thoroughly. So 2.1 cos 30 works out to 1.82. kilometers. And that gets me my north component. This is 1.82. And now I'm going to do my east component. That's going to be your sine because it's your opposite in your hypotenuse. The easiest mistake to do when doing these questions is to switch which component is which. This is actually the second time I'm recording this video, because the first time I recorded it, I wasn't paying enough attention and I made that mistake. I'm going to show you as we go through the diagram a simple way, hopefully, for you to avoid making the same mistake that I made that is leading me to have to redo this video. Specifically, what I mean is if you put your values on your triangle, it gives you a secondary opportunity to see if your values make sense. This angle here is 30 degrees. That's an acute angle. That means that the opposite should be lower than the adjacent. If you switched your components, that'll be wrong. And if you draw your triangle just a little bit to scale, it doesn't have to be totally to scale, but just a little bit to scale, then I think you'll see when you go to do this that the smaller component is on the smaller side and the bigger component is on the bigger side. It doesn't have to be perfectly to scale to see that. Okay, now looking at D2. D2 is 1.5 kilometers east. I don't have to break that into components. If I go to draw that vector, it's already sort of in components. It's all in one direction. So I don't really need to do anything with that, but I will sort of recognize that delta D2 in the north or south direction, whichever way you want to look at it, is 0. If it's going all east, it's not going north or south at all. That's just something to recognize. Now the last one. 1.5 kilometers west, 20 degrees south. So this is good practice for us to see how to draw these vectors one more time. I'm actually going to go down here and then all the answers will hopefully be somewhat close to each other. West, then south. See? West, then south. And you always put your angle where you started. The magnitude here is 1.5 kilometers. So this is my opposite and this is my adjacent, and I should label this delta D2 like that, and then that's well labeled. So this would be, I don't know what happened there for a second, delta D2 south, and this would be delta D, I keep saying 2, but I mean 3. Delta D3, delta D3. West. So this one, the opposite one, is the one that gets the sine. So sine 20 equals delta D3 south over 1.5 kilometers, or opposite over hypotenuse. And if I multiply both sides by 1.5 kilometers, again, every time it's going to work out to the same magnitude times a sine or times a cos. So if you want to skip to that step, as long as you don't mix up which one's which, it's okay. So this delta D3 south is going to be 0.513 kilometers. And now the other one's going to be the cos, which is adjacent over hypotenuse. The adjacent here being D3W over 1.5 kilometers is equal to the cosine of 20. Multiply both sides by 1.5. I got 1.41. 1.41 kilometers, and that's your delta D3W. Now I highly recommend at this point, if you haven't noticed, we've got a lot of numbers on the go. 1, 2, 3, 4, 5 different numbers that we have to all summarize, and we want to get them all right. So what I'm going to suggest to you is make a chart, and be careful making this chart because it's easy to make mistakes when transferring the information. Label your chart with headings that represent what you consider to be the positive direction. So I'm calling north and east positive. And then use a column over here to include what the information represents. So delta D1, delta D2, delta D3 in this particular example. So I've got 1.82 kilometers, and it's north, which means I'm going to leave it as a positive. This one's 1.05 kilometers. It's east, so I'm going to leave it as a positive. I don't know what happened there. East. There we go. Delta D2 is a relatively straightforward one. He's all east, which is my positive direction, no north or south. So for delta D2, I have 0 in this direction and 1.5 kilometers in what I consider to be the positive direction. And then finally for delta D3, I didn't do my little trick that I mentioned before, so maybe I'll just pause and do that for a second here. What I said was transfer the values to the diagram and see if it looks like it makes sense. 0.513 kilometers here would be the south component, and 1.41 is the west component. Now 20 degrees is a small angle, so what that means then is that this 0.513 is smaller than this 1.41. Again, I haven't gotten a protractor or anything, but I drew a little bit to scale, and what I can see is that this side here is a little bit smaller than the side here, and so these numbers make sense. I haven't reversed them, which is the biggest problem you're going to have. One more thing to be careful of though, remember we have positive directions and negative directions. That 0.513 is in the south direction, and I've declared north as positive, so I need to be careful to include it as a negative. That 1.41 is west, and I've called east positive, so it's negative 1.41 kilometers. Finding the total of those two things, 1.82, I guess technically plus a minus, but it works out to just minus 0.513. I get 1.307 kilometers, and in this direction 1.05 plus 1.5 minus that 1.41, I get 1.14 kilometers. Now, what does that mean? North, then east. 1.307 kilometers and 1.14 kilometers. Now I've drawn this in the order that would sort of be considered the polite order. Because this component is a little bigger than this component, I usually put this one first. You don't have to do that. I will try and do that in all of my examples so that they're all consistent, and then you have a consistent approach where you can get the exact same answer that I get. But if you do it the other way, it's not that big of a deal. To get the result in here, I'm going to use the Pythagorean theorem. So a squared plus b squared square rooted. This is just calculator work. Square. Got 1.73 kilometers. And now I want to get this angle. This one's my opposite, and this one's my adjacent. So if I'm going to use my opposite and adjacent, that means I've got 1.14 kilometers divided by 1.307 kilometers. And I can get an angle using my inverse tan. Again, I think I mentioned this in a previous video, but make sure that your calculator is set to degrees. We're doing everything in degrees. If you can do all this in radians, of course, but you want to make sure your calculator is set to what you're trying to do. So that means it's north. See, I went north here first, then east. So it's 41.1 degrees east, north of east. If you had done this triangle the other way, so you'd gone east then north, you'd have this angle right here. If we look at this carefully, we can see the angle we got, theta, and this angle, alpha. Theta plus alpha would be equal to 90 degrees. So if this is 41.1, alpha would be 48.9. However, we would have gone east, then north. So another acceptable heading for this vector is 48.9 degrees east, 48.9 degrees north. Either one of those answers are acceptable. So that's it, adding the displacement of three different vectors.